Hi, and welcome to another video of the video series of myself looking at websites from quantum technology companies, including quantum computing, quantum sensing, and quantum communication. I almost forgot about the third one. Today we are looking at Alice and Bob, which is a European company in the space of quantum computation. Everything else we will see from the website. So first look at the website, very beautiful. We see some physicists writing formulas, wafers being produced and fabricated, bonding, cryogenics, here we see a cryogenic fridge, and then we see some controls of this fridge, and then I think these are the founders. Very cool. So very nice animation, a very good start into the website. It says building the first universal quantum computer, and then this is humanity's next challenge. And indeed, it is a big challenge. And now let's see what else we can find out here on the website. So they raised 100 million euros. That's quite a lot of money. They published their roadmap all the way to 2030. And we also see they published a white paper. But we will not look into any of those news yet, because for now, we are looking at what the website actually says. So here it says the mission again: build the first universal and fault-tolerant quantum computer by designing superior qubits. So what do we take away from that? They actually have a different approach to the qubits than the competitors that we looked at. But how is it actually different? Let's see what we can find out here. So we see a black dot. Nature's quantum at its most fundamental level, like atoms, for example. Yes. And these atoms, they pair together. Our classical world emerges from the quantum one. Yeah. So if you put a lot of atoms together, you end up with a classical object. Okay. That is inaccessible to our eyes. Okay. That's interesting. But we still need to figure out what they're actually making, what is making them unique. Accessing the quantum world will require a quantum computer. True. So this is the quantum computer here in the background. Or basically this is a cryostat, and then down here will be the quantum chip, I guess. Okay, so here again, what makes them different, I guess. Today's quantum computers don't work. Their basic building blocks, qubits, are too fragile. Disturbed by our noisy classical world, they run into errors. They decohere. We must design better qubits. So now let's take a very quick step back before we go on with this discussion here. Maybe a quick comment. So we've seen some other companies before in this series here, which are showing different types of qubits, like ion traps. We've seen superconducting ones. There will also be other architectures, and most of them, they are so-called NISQ system. So they basically have errors attached to them. Those errors come due to the operation, they come due to the interaction with the classical world, what we saw here, so noisy classical world, and that leads to decoherence. There's a way of correcting that, which is called the quantum error correction, which is a whole discipline in itself. But basically what you can do is you can use a lot of those NISQ qubits, so qubits with error, chain them together in a very, let's say, intelligent way. And then by doing so, you can figure out if they are prone to some specific errors, if there is some noise and decoherence happening, and then you can basically correct for that. This is what this quantum error correction is doing. This is much more difficult than for classical computation, because in the quantum world, you cannot copy information. There is a non-cloning theorem, so information can not be copied. And that means if you want to do this quantum error correction, you are not allowed to touch the actual information, but you have to basically infer from this collected system of qubits whether there's an error or not. Now here, in the case of Alice and Bob, they say, let's forget about all of that. Let's come up with a qubit that doesn't have any of these issues, that is not prone to any errors. So that's the specific thing the different philosophy that we see here. So the idea is to build qubits that are not prone to this, that are better. And of course, I'm very interested to learn how they actually do that. So they say we pioneered the cat qubit, the first qubit with built-in error correction to make quantum computers useful. So I guess that's what we see here with the nice cat logo or the Alice and Bob logo on it. This is the cat qubit, and that's the one which, will have built-in error correction. Of course, I'd be very interested to see how that works in detail. But maybe that would be too much of a jump now. Let's first of all see what they have here. So solution, the box is our team of experts to get you ready to discover, identify, and say already quantum advantage opportunities for your business. And then there's Fels Cloud. Okay, we see here the blog post with the latest blog posts from the company, and then media that has already been covering them. And there's a couple of big names. So we see here the IEEE Spectrum, Le Monde is a French magazine. We see Reuters, Physics World. So a lot of big press coverage already in here. Okay, and with that, let's move on to the next subpage. By the way, just as a comment, I love those really those nice, let's say, artsy elements that they put on the website, which makes it also a little bit more toyful and nice to look at, I'd say. Just my personal opinion. What do you think? Write it down in the comments below. Harnessing quantum nature. So a qubit can be 0 or 1, 0, 1, or somewhere in between, thanks to the fundamental laws of quantum mechanics superposition. Okay, so there's superposition explained. Then we have the Bloch sphere here with the two poles. And then we have the plus and minus states. Okay, makes sense. So humans do not experience quantum for a reason. Everything is perturbation for a qubit. So you have bit flips, you have phase flips. Okay, and then you have basically the decoherence. So that's the problem, quantum errors. The cost of error correction, that's what I said before. You need a lot of those qubits to build an error correction. And then if you could do it before it actually happens, Alice and Bob's cat qubit does exactly that. Our pioneering approach is bit flip protection. So they basically have a built-in way of protecting for this. We deal only with one class of errors, the phase flip, reducing quantum error correction to one dimension. Simple. Thanks to this, a logical qubit could be assembled using as few as 4 physical cat qubits. Such a low overhead helps us lead the race to building a fault-tolerant quantum computer. So now that's very nice. They explain the different mechanisms here of errors that can occur, and then they basically explain the error correction that they have intrinsically in the qubit and why this is a game changer. Here it says 100 logical qubits by 2030 is on their roadmap. And then, there's also some papers here, which I guess will explain how these qubits actually work. For the sake of time, we will not go into these for now. But again, if you find it interesting, if you want me to look at one of those papers or all of them, just let me know in the comments down below, and then we can take a look at those together. There is something here on the tech. They are quantum designers. Here's something about the fault tolerance again. We see the different, let's say, qubit architectures. So it starts with boson, hydrogen, helium, and lithium is next. So this is inspired by the periodic table. If you click on it, we can even see what it looks like. So here, I guess we have the RF connectors all around here, where the coax cables will be connected. And then the signal is going all the way towards the chip in the center, which might be bonded in a specific way, maybe wire bonds, don't know. And then we have here probably the actual qubits of our system. Very nice. Here is the previous chip, and here is the first chip. Ooh, that's quite zoomed in here. Yeah, you can see some superconductor cavities or lines here. There's already the logo on it. Very cool. So yeah, love it. I actually like the fact that there is so much to discover on this website here. So then it explains how the whole iteration works, how they basically come from the design to the verification, or from the ideation to the verification. So this is like a smart design process. Okay, and here we have some numbers on what they've actually achieved so far. Yeah, here we see AutoCAD, Tomcat, Mooncat. So this is probably the qubit architecture that they've come up with. And yeah, then there is some videos down here which also talks a little bit about the people apparently. Very nice, very nice. We cannot check these out now because otherwise I think it will become a too long video. Okay, there is something more here. Okay, there you can see the team. Lots of smart guys and girls, of course. Then we have something about the cloud here. So I guess that's access to their hardware via the cloud. Yeah, it says test quantum hardware, test it. So I guess it says Google Cloud. So this is running on Google Cloud. We have seen other ones with Microsoft and Azure, with Microsoft Azure and AWS before. Here we see this is running on Google Cloud. And you can also emulate it. So there's probably like a emulation of the system, which you can, I guess, run on your computer. It says free and open source. Very nice. Always good if things are open source. It makes it very much more transparent. There are also some partners here, like cloud partners. And then it says take a front row seat at the quantum race. So here you get access to the community. They have a community on Slack where you can, I guess, ask your questions, talk with people. If you run into problems trying to set something up on the cloud, that's where you want to go. Then that's us. Yeah, that's very sympathetic. You can see the whole team here on the website. And there are quite a lot of people already, but I mean, they also have a bit of funding. So I guess it makes sense. Building these new types of qubits is nothing that you can easily do. So you need a lot of people. Yeah, 120 plus people, 2 offices, 24 nationalities, so very international. And 45 plus PhDs, 100 million plus euro, and 88 out of 100 in the gender parity score, whatever this is. I'm not sure about it. Then there's some story about how the company is born. Here you see the 2 founders, I assume. And then you can probably go through the whole story. Then there is something about the values that they have. Okay. I like it. I mean, it's a very unique way of positioning also the company. Also compared to the other ones. This has, let's say on the website, it gives it a very nice character also when you put all of these things there. Here it says something about the investors. So you see the European Innovation Council, but there's also some private investments, like I guess Supernova Invest is a private one. Very nice, very transparent. There's also the roadmap, which we saw before. You remember the 2030 statement about the 100 qubits will probably somewhere be here. I like the illustrations. It makes it, again, I think it gives it a character. I like that quite a lot. And yeah, here we have the 2030 again, the useful quantum computing. Let's hope they can achieve it. I mean, I'd be very interested. and probably not only just myself. And yeah, there's white paper as well, which explains it's transmon based. So transmons and cat qubits seem to be related in a way. So yeah, and there's the roadmap again. I think with that, there's some more resources here. You have a blog, publication, newsroom, and the white paper. Go check it out if you have more time than we have right now. I will definitely also put the link to the website down below the video. With that, thanks again for joining me on this adventure of exploring quantum technology companies' websites. Looking forward to see you again in the next one. With that, make sure to subscribe to the channel and then see you next time, and always stay hydrated. Bye bye.